Hi everyone, in this video we're going to take a look at scientific notation. It's also called standard form or the standard index form. So what this basically is a way to represent a really big or a really small number. So let's look at some examples. If I have 200, how would I represent that in scientific notation? So the first thing you need to know is scientific notation is in the form of n times 10 to the n, let me say. And this value of this n here, it has to be between 1, okay, so it's greater than 1, but less than 10. And the thing about this is it can equal 1, but it can't equal 10. Okay, so what am I talking about? Let's take a look. So for 200, in order to represent that in scientific notation, we need to make 200 such that it is a product of two numbers, one of them being 10 to the power of something. So 200 can also be written as 2 times 100, right? So we have our first value here, 2. And 2 indeed is greater than 1 and less than 10. So this would be a correct answer, correct value for n. So 2 times 100. Now 100, we need to represent that as a power of 10. Okay, and we know that 100 can be written as 10 to the power of 2. Now if you don't know how to work with exponents, I have a video for that. So make sure you pause this, go check that out first, because an understanding of exponents is really important before you can understand scientific notation. Okay, so 100 here can be written as 10 to the power of 2. So 200 in scientific notation is just going to be 2 times 10 to the power of 2. Okay, so that was simple. Let's look at another example. What if I have some really big number? I have 6, 3, 1, 2, 3, 4, 5, 6, 7. Okay, I think I'm going to stop there. Okay, so if I have some really big number like this, how am I going to express that in scientific notation? Again, it has to be product of two numbers, one at the value of n, which is greater than 1 and less than 10, and the other being a exponent of 10 raised to some power. Now, this can be written as 63, right, times 10 to the, and then you just count the zeros. You have 1, 2, 3, 4, 5, 6, 7 zeros. So 63 times 10 to the 7 is this number. But if you notice here, 63 is not less than 10. 63 is much bigger than the value that x can be. So it doesn't fit our range. But what does fit our range is if we make the 63 a 6.3. So if this 63 becomes a 6.3, then it will fit our range. So what we're doing now is we're going back another decimal. So we have to make this, if we make the 6.3, we have to raise that to another exponent. So that becomes 10 to the 8. So our answer would be 6.3 times 10 to the 8. And you can just count that, you can check that. So if I put a point here and I want it to go there, so you can count, that would be 1, 2, 3, 4, 5, 6, 7, 8. So my answer is 6.3 times 10 to the 8. Okay, let's do another example. What if I have a number 3, 9, 4, 4, 5.87, okay? Now you're probably like, wait, how do I make this here? It was all just zeros. So it was easy for us to write this as 10 to raised to something. But what do I do if I have something like this? Okay, now you have to follow the exact same method. We need it to be a product of two numbers. So instead of directly just counting the zeros, which we can't do here, let's first decide what our x is going to be, or the n, right? well, I should just write this as n, maybe. That would make it a little easier. I don't know why I put the x in there. So this is actually going to be n. So we're saying that the value of this n can be greater than or equal to 0, but less than 10. Okay, so how would we solve this problem? Now, let's first decide what our value of n can be. N definitely can't be 3,945 because that's much, much greater than 10. So looking at this number, the value that will fit our range here is going to be 3 points, right? 3.94587 can definitely fit the range. If we do 39, if we decide to shift the decimal here and we do 39.45, then that still is much, much bigger. So we have to go back and we have to put the decimal here because this would be the only value which would fit the range. So if we make this number 3.74587, then this value of 3.94587 raised to times 10 to what power is going to give us the original number? So we need to say that 3.94587 times 10 to some power is going to return us the value of this, which was the original number given. So all we're doing is we're converting this number into another form, but ultimately this has to represent this number again, right? So we're saying 3.94587, sorry, I'm saying the number a lot, but this number times 10 to some power has to give us back this. Now our decimal is currently after the 3, but we wanted to move 3 places to the right and go back after 5 here. So in order to do that, it has to move 3 places to the right. 1, 2, and 3. Okay, and when you want the decimal to move to the right, your power has to be positive. So you're making it a positive 3. Okay, so this in standard form is going to be 3.94587 times 10 raised to the 3. And if this moves 3 decimals, it's going to give us back the original number. Okay, now what if I have a really small number? I have 0.00000034. What would I do? If I have such a number, then what I'm going to do is, again, I have to make it, remember, n times 10 raised to the m, and this value of m has to be less than 10 and greater than or equal to 1. So in such a situation, it will again be easier for us to first figure out what this n is going to be. So here, the value of n has to be something based on this digit, the 2 digits we have here, because it has to be greater than or equal to 1, and these are the only 2 digits in this whole number which are greater than or equal to 1. So if we put the decimal here, now just ignoring these zeros for a second, we have 34. Now 34 is much, much bigger than 1 and bigger than 10. So we need our value to be 3.4, right? So we decide that our value is going to be 3.4. Okay, 3.4. Now this times 10 to what power is going to return me this original value here? In order to do that, I need this decimal, 3.4. So the decimal currently, we moved the decimal from here to here, and we made it 3.4. But 10 raised to what power is going to move the decimal back here. So in order to do that, the decimal has to go 1, 2, 3, 4, 5, 6 places to the left. And if you want the decimal to move to the left, it has to be a negative power. So this is going to be 1, 2, 3, 4, 5, 6. So negative 6. Okay? So this number in scientific notation is going to be 3.4 times 10 to the negative 6. Now let's look at a problem. How would I solve this if it's in a question? So here it says, what is the area of a tiny rectangular chip measuring 0.00026 meters long and 0.00015 meter wide? Now, if you had a calculator, obviously you could just punch these numbers in. But what if this was on a non-calculator paper? Okay, so what you could do is first, I'm going to write down the data I have, 0.00026, and I have 0.00015. And the first thing I want to do is I want to convert these values, both of these values, into scientific notation. Okay, so again, we're going to follow the same method as we did here. So we want it to be n times 10 to the something, and n has to be greater than or equal to 1 and less than 10. I know I'm saying this a lot, but this is really important. Okay, if you don't understand this or if you don't remember this, then you will not be able to make up your scientific notation. So it's really important to know this. Going back to the problem, how I would make this a scientific notation, again, I want to first decide what my value of n is going to be. And here, the only option, the two value digits I can work with are 2 and 6. 26 by itself is too big, and if I want to make it 0.26, that's too small. So I will have to put the decimal here and make it 2.6, right? 2.6. Now that times 10 to some power has to return this value of 0.00026 to me. And in order to do that, I need the decimal to move 1, 2, 3, 4 places to the left. And remember, if you want it to move to the left, your exponent has to be negative. So negative 4. Sorry, negative 4. Okay, so that would be the scientific notation for this. And for this one, we have 0.00015. And again, we have to first decide what our value of n is going to be. The two digits here I can work with are 1 and 5. Now 15 by itself is too big, 0.15 is too small. So I have to put the decimal here and make it 1.5, right? 1.5, and that times 10 to some power has to give me back this value. So if I put the decimal here, I need it to move 1, 2, 3, 4 places to the left. And if I wanted to move to the left, it has to be negative. So this would be the standard notation of this. Okay, so this is just the first part. We haven't even begun solving the question yet. So the question is asking me, what is the area of a rectangular chip? Now, if I just quickly draw a rectangle here, this is my length, this is my width. Area is just length times the width. So here what I want to do is I want to multiply these two values, but how I'm going to do this is first you want to just ignore these the powers and just concentrate on the numbers. Okay, so the numbers we have are 2.6 and 1.5. So what I'm going to do is I'm just going to say area equals. The first thing I want to do is 2.6 times 1.5. So just focus on the numbers or the n you have and multiply the n's together. And 2.6 times 1.5, you could work this out here. You could work this out. But just for time's sake, I'm just going to put the value in. It's 3.9. Okay. Now this times the second step you want to do is you want to multiply the powers together. 10 times negative 4 times 10 to the negative 4. Here again, if you don't know how to work with exponents, make sure you understand that first, watch the other videos, and then come back to this. Because here we are going to apply one of the exponent laws. 10 times negative 4 times 10 times negative 4. When you have the same base, all you have to do is you have to add the exponents. So this is going to be 10 times negative 4 plus negative 4, which is 10 to the negative 8. -8. And that is my answer. Thank you.